Now I am going to start chapter 4. This chapter is devoted to the elliptical partial differential equation. I shall take Laplace equation and Poisson equation for this discussion because these equations come in many fields of mathematical physics like electrostatics, magnetostatics, surface waves in fluids and motion of gravitation, motion of particle in gravitation, etc. And I shall show that there is an important role of boundary condition in the solution of Poisson's equation and Laplace equation. So, it is important to discuss about the boundary condition together with the solution of a Laplace equation. Thus, the entire chapter is divided into 3 modules. In module 1, I shall discuss about different boundary conditions. Apart from that, I shall discuss about harmonic function and its application, and I shall also discuss how to derive Laplace equation in different coordinate system. Now, I am going to the first slide of module 1. The Laplace equation with n independent variables can be written as grad square psi equals to 0, where the domain of the function is the set omega, which is subset of Rn. The equation is written in equation number 1, and the Poisson equation is written as grad square psi equals to f, where the function psi and f are defined over the domain omega, which is subset of Rn. The operator del square is defined as del 2 del x1 square plus del 2 del x2 square plus del 2 del xn square. It is to be noted that Cauchy problem for the Laplace equation is not well defined, because the Cauchy problem for Laplace equation in a bounded domain V is overdetermined. We cannot specify both psi and its normal derivative del psi del n on the surface S of the bounded domain capital V. Thus, we have to choose either the value of psi on S or the value of del psi del n on S. Now, according to the boundary condition, we can categorize the problem into 4 categories. Now, according to boundary condition, we can divide the problems into 4 categories. So, now I am going to discuss about Dirichlet problem. Dirichlet problem is defined as following. Let small g be a continuous function prescribed on the boundary S of a bounded region capital V. Then the problem is to determine a function psi, which is function of 3 independent variables x, y, z, satisfying the equation grad square psi equals to 0 at any point within V and on the boundary of V, that is on S, the value of psi is equals to the function g. This problem is known as interior Dirichlet problem. On the other hand, we can define an exterior Dirichlet problem. In exterior Dirichlet problem, the function psi will satisfy grad square psi equals to 0 outside the region V, where capital V is a finite simply connected region, and on the boundary of V, that is on S, the condition psi equals to g. So, this case we call the problem as exterior Dirichlet problem, and the Dirichlet problem is referred as a first boundary value problem. Now I am going to discuss about Newman problem. So, in Newman problem, the function psi will satisfy the equation, the Laplace equation grad square psi equals to 0 within V if it is an interior Newman problem and its normal derivative del psi del n equals to some function h at every point on the boundary of V, that is on S. Similarly, we can define exterior Newman problem. For exterior Newman problem, psi will satisfy the equation grad square psi equals to 0 outside some region capital V, and on the boundary of capital V, the normal derivative of psi, that means del psi del n, is equals to some known function capital H. So, any kind of Newman problem, it may be an interior problem or exterior problem, is called a second boundary value problem. Now, I shall tell about Churchill problem. In interior Churchill problem, we want to find the value of the unknown function psi which satisfies the equation grad square psi equals to 0 within some bounded domain capital V, and on the boundary, that means on S, del psi del n plus g psi equals to f, where the functions f and g are some continuous function and they are defined on S. So, in case of Churchill problem, the boundary condition is different from the previous cases. When the boundary conditions is given in this form, that means on the boundary the function, the sum of the function psi and its normal derivative is defined, then it is called Churchill problem. In the similar way, we can define exterior Churchill problem, and Churchill problem is also called a third boundary value problem. Now I am going to discuss about Robin problem. For interior Robin problem, we mean we have to find an unknown function psi which satisfies the equation grad square psi equals to 0 within a finite domain capital V, and on the boundary of capital V, that means on S, psi is equal to f1 on S1 and del psi del n equals to f2 on S2, where S is the union of two boundaries S1 and S2. In the similar manner, we can define exterior Robin problem. Robin problem is also referred to a mixed boundary value problem or fourth boundary value problem. It is to be noted that the boundary value problem associated with Poisson's equation can be formulated in a similar way. In this section, we are going to discuss about harmonic function and its properties. A function psi is called harmonic at a point x, y, z if it satisfies the Laplace equation. That means, in case of three independent variables, the equation is del 2 psi del x square plus del 2 psi del y square plus del 2 psi del z square equals to 0. A function psi is said to be harmonic in a domain if it is harmonic at all points in that domain, and a function is said to be harmonic in a closed region R if it is harmonic at all interior point of that region. So, in this section we shall discuss harmonic functions and its properties. Apart from that, I shall discuss the mean value theorem on harmonic function, and lastly I shall discuss about maximum minimum principle and its consequences. So, for the discussion we have to go to slide show. I have already defined a harmonic function. Now, I am going to discuss some properties of harmonic function. The first property, it is written here, if a harmonic function vanishes everywhere on the boundary of a domain, then it is identically 0 everywhere. Proof is also given here. Let psi be a harmonic function. So, grad square psi equals to 0 in a domain V, and it is given that the value of psi equals to 0 on the boundary S of V. Now, using Green's identity, we can write integration over the volume V psi grad square psi dV plus integration over V grad psi whole square dV is equal to surface integral of psi del n over the surface S. Now, we have to note that grad square psi equals to 0 in the domain capital V and psi equals to 0 on S. So, if we use the condition grad square psi equals to 0 in V, the first integral in the left hand side is equals to 0. Now, using the condition psi equals to 0 on S, the right hand side of the integral is 0. So, the above equation reduces to the form integration over V grad psi square dV is equal to 0. Since psi is a real quantity and grad psi is also a real quantity, so this implies that grad psi must be equals to 0. This also implies that psi must be equals to constant in the domain V, but psi is continuous in the domain V and the boundary S, and in the boundary we know that psi takes value 0. So, psi must be equals to 0 in V using the continuity condition. So, this property is proved here. Similarly, we can prove the another property. This is property number 2. If a function psi is harmonic in V and del psi del n equals to 0 on S, then psi is a constant in the domain V. This property can be proved in the similar way as we have done to prove the property number 1. Now, I am going to discuss third property. It says that if the Dirichlet problem for a bounded region has a solution, then it is unique. I shall prove this property here. So, if possible, let there are two different solutions psi 1 and psi 2 for the interior Dirichlet problem. That means, psi 1 will satisfy the Laplace equation grad square psi 1 equals to 0 in V and psi 1 equals to some known function g on the boundary S, and there is another solution psi 2 which will satisfy the Laplace equation grad squared psi 2 equals to 0 in V and psi 2 equals to G on S. Let psi is equal to psi 1 minus psi 2. So, grad square psi is equal to grad square psi 1 minus grad square psi 2. So, its value equals to 0 in V, and this psi will satisfy the boundary condition psi on S equals to psi 1 on S minus psi 2 on S. So, that equals to G minus Z, that means equals to 0 on S. Now, if we recall property number 1, from that property we can say that the solution of the equation grad square psi equals to 0 in V and psi equals to 0 on S is psi equals to 0 on V plus S. That means psi 1 is equal to psi 2 on the domain V as well as on the boundary S. So, this implies that the interior Dirichlet problem has a unique solution. This property can easily be proved in case of exterior Dirichlet problem also. Now, this is property number 4. It is regarding Newman problem. It says that if the Newman problem for a bounded region has a solution, then it is either unique or differs from one another by a constant. So, proof is given here. If possible, we assume that there are two distinct solutions psi 1 and psi 2 for this Newman problem. This implies grad square psi 1 is equal to 0 in V and del psi 1 del n equals to some known function h on S, and psi 2 will satisfy grad square psi 2 equals to 0 in V and del psi 2 del n equals to h on S. In the similar manner, we assume a function psi which is difference of the above two functions psi 1 and psi 2. So, psi equals to psi 1 minus psi 2, and if we see grad square psi is equal to grad square psi 1 minus grad square psi 2. So, its value is equals to 0 in V, and if we take the normal derivative of psi, that means del psi del n on S, its value is equals to del psi 1 del n minus del psi 2 del n. So, that is equals to h minus h equals to 0 on S. Again, using property 2, we can conclude that psi equals to constant on V plus S. If the constant is 0, then psi 1 is unique. That means psi 1 is equal to psi 2 in V. So, this proves this property. So, for this case psi, the solution may be unique or they may differ from one another by a constant. Now, I am going to define spherical mean. Let V be a bounded region enclosed by a closed surface S and P be a point within V. So, figure is given here. So, P is a point which has coordinates x, y, z, and around P we are drawing a sphere of radius small r, and the surface of the sphere is denoted by sigma, and we have drawn the circle or sphere in such a way that sigma lies entirely within V, then if psi be a continuous function in V, its spherical mean is defined as psi bar r is equal to 1 divided by 4 pi r square surface integral of psi d sigma. That means we are taking the integral over the surface of the sphere sigma, and q is any variable point on the surface of the sphere sigma, and d sigma is the element of surface. So, this is nothing but average of the value psi over the surface of the sphere sigma. Now, I shall state one important theorem which is known as mean value theorem for harmonic function. This theorem states that suppose the function psi is harmonic in a bounded region V and P be a given point in V, then sigma, let sigma be a sphere with center at P and radius r, such that sigma lies entirely within the domain, then psi at the point P is equals to the psi bar r, which is the spherical mean of the function psi over the surface sigma, where sigma is a sphere of radius smaller and with center at the point P. Now, there is one important theorem which is known as maximum minimum principles, and this principle can be proved using the property of harmonic function. First, I shall state the theorem and then I shall prove this theorem. So, this theorem states that if psi be a continuous function in V plus S and it is harmonic in the region V, which is bounded by the closed surface S, and we also assume that psi is not constant everywhere on V plus S, then the maximum and minimum values of psi must occur on the boundary. Proof: if possible, we assume that psi attains its maximum value m at some interior point P of V. Since psi has a maximum at P, we can construct a sphere sigma about P of radius r such that sum of the values of psi on sigma must be less than m. This is the property of having maximum value of a function. Since this is a local maxima of psi, now again using the mean value theorem, the value of psi at P is the spherical average value of psi on sigma, and therefore, its spherical average is less than capital M. So, it contradicts the fact that it will have the same value as it is at the point P. Hence, psi must be constant over the entire sphere sigma. Now, suppose Q be another point in the domain capital V. Now, we connect the point Q with the point P by an arc such that the arc lies entirely within the domain V. Now, by covering this arc with spheres and using Heine-Borel theorem for choosing a finite number of covering spheres, we conclude by considering the above argument that psi has the same constant value at Q as at P. Hence, it is impossible for psi to attain its maximum value at any point inside V. So, it implies that phi must attain its maximum value at some point on the boundary S of V. So, a similar argument shows that psi attains its minimum value on S. So, in this theorem we learn that maximum or minimum value of the function psi is attained only on the boundary S of the domain V. Now, there is another important theorem which is called stability theorem, which says that the solution of Dirichlet problem depend continuously on the boundary values. Proof: let psi 1 psi 2 be two solution of Dirichlet problem satisfying the equation grad square psi 1 equals to 0 together with the boundary condition psi 1 equals to g1 on the boundary S, and the another solution psi 2 will satisfy the Laplace equation grad square psi 2 equals to 0, and it will also satisfy the boundary condition psi 2 equals to g2 on the boundary S of the region capital V. Now, we construct a function psi which is equals to psi 1 minus psi 2. Now, if you think about the equation satisfied by the function psi is grad square psi is equal to 0 in the region V and psi equals to g1 minus g2 on the boundary S of the region V. Now, by maximum minimum principle, psi attains its maximum and minimum values on S. S is the boundary. Hence, at any point within V, we have for any given epsilon greater than 0, minus epsilon less than psi minimum is less than equals to psi less than equals to psi maximum, which is less than epsilon. That is, mod of psi is less than epsilon if the difference of the psi max minus psi mean is less than epsilon. Or in other words, we can say that if g1 minus g2 mod is less than epsilon on S, then mod of psi 1 minus psi 2 will be less than epsilon in V. So, it says that the solution in V depends on the boundary conditions, which is in this case mod of g1 minus g2. So, in this way we prove this theorem. The solution of Dirichlet problem depend continuously on the boundary values. It is sometimes required to find solution of Laplace equation in different geometries. In this section, we shall derive the expression of Laplace equation in different coordinate systems like polar coordinate system, spherical and cylindrical coordinate system. So, for derivation, we need to go to the slide show. Now, I am going to derive Laplace equation in plane polar coordinates. In polar coordinate system, there are two independent variables r and theta. So, here we are trying to write the Laplacian operator grad square in terms of the independent variables r and theta. The derivation is shown here. The corresponding transformation is x equals to r cos theta and y is equal to r sin theta. So, from this transformation we can derive that r square equals to x square plus y square and theta equals to tan inverse y by x. The Laplace equation in Cartesian coordinate is written in equation number 5, psi xx plus psi yy equals to 0. Now, to write that equation in terms of r and theta, we have to compute psi x. So, psi x equals to psi r r x plus psi theta theta x. Here we have used chain rule. So, that is equals to psi r into the value of r x is cos theta minus psi theta into sin theta by r. Here we have put the value of theta x as sin theta by r. Similarly, we can derive the value of psi y using chain rule. Psi equals to psi y is equals to psi r r y plus psi theta theta y. So, this equals to psi r into sin theta plus psi theta into cos theta by r. So, here we have used the value of r y and theta y which are given here. So, if you take the second order derivative of psi x with respect to x, in the similar way we can find an expression for psi xx, and in the similar way if we take the second order derivative of psi with respect to y, that means if we compute psi yy in terms of the derivative of psi with respect to r and theta, and if we substitute those value in equation number 5, we will get an equation which is written here psi rr plus 1 by r squared psi theta theta plus 1 by r psi r equals to 0. The derivation is not shown here. If anyone is interested, they can go through the e-text of this module. The detailed calculations are there. So, we get equation number 6. This is the Laplace equation in plane polar coordinates. Now, this is the derivation of Laplace equation in cylindrical coordinates. In cylindrical coordinates, there are 3 independent variables r, theta and z, and in the similar way, so we can derive the expression for Laplace equation in terms of the independent variables r, theta and z, and this is the relation between Cartesian coordinate and the cylindrical coordinates is x equals to r cos theta, y is equal to r sin theta and z is equal to z. So, using this transformation, one can transform the equation 7 to equation 9. The detailed calculation can be found in e-text. This is the last one. Here we have derived Laplace equation in spherical polar coordinates, and the corresponding transformation is x equals to r sin theta cos phi, y is equal to r sin theta sin phi and z equals to r cos theta. So, using this transformation, we can derive the expression for Laplace equation which is written in equation number 10. Thus, in module 1 of chapter 4, we have discussed about different type of boundary value problems, namely Newman problem, Dirichlet problems, Robin problems, etc. We have discussed about harmonic functions and its properties, and we have also discussed about maximum minimum principle and its consequences, and lastly we have derived the expression for Laplacian operator in different coordinate systems. In this way, we end this module.